Hello friends, welcome back my YouTube channel MS Maths. In this video, I'll discuss subgroups, counting of subgroups, subgroups of different groups. For example, Zn cross Zm, Dn and Sn and Q8. Okay, and also we'll discuss the product of two subgroups. How can we find the product and how can we find the subgroup of the product group also, that we'll discuss. This is helpful for IIT JAM, CSIR-NET and GATE. My name is Manoj Solanki and let's start the video. In this video, we'll discuss subgroup. So we'll start with the definition of subgroup. What is the definition of subgroup? Okay, so subgroup is basically a subset. Okay, if you have any group, let's say my G star is any group under composition star, that is known as binary operation, and if let's say any H which is subgroup or which is subset of G, it will be the subgroup of G. Now it means it should satisfy some properties. What are those properties that we will see here? So first of all, if you have any subgroup or any group, any non-empty group, let's say G star, G is a non-empty and where H is a non-empty subset of G. So I'll just simply write H is a non-empty subset of G. Then this H is said to be subgroup. This H is said to be subgroup of G if and only if this H itself is a group under the same operation. That's the meaning of this. H itself a group under the same composition or same operation, we can say. So from here we can say H star is also a group, okay, under same operation. Now what do you mean by same operation? Whatever the operation we are taking in group, subset is H. Okay, so if it is again a group, means it should satisfy four property. First property is what? Closure law. Okay, second property is associative, and third property is existence of identity, same thing, and third property is inverse for each element. If all four property holds for this set of G and this is again a group, then we will simply say this is a subgroup of G. But the condition, necessary condition is what? It should be the subset of G. If it is not subset, then we can't talk about the subgroup of G. We'll take some examples of this. Okay, first example, let I have Z, okay, which is subset of Q, and we know that Z plus is a group. We know that Z plus is a group. Then simply we can say that Z plus is subgroup of Q plus, where Q is nothing but rational, set of rational number. Now taking the second example, let's say phi is not equals to Q, means it is a not subset of this. Okay, and then simply we'll write from here it's a subset of R by C, and we'll write Q plus is a group. Q plus is a group. Then Q plus is subgroup of, okay, where Q is a subset of R and Q is subset of C. So simply Q is nothing but a subgroup of R plus and C plus, means a group of complex number. Okay, so these are some examples here. Now from here there is one more concept, that one step test of subgroup. What is the meaning of one step test? If you have any group, let's say Z star, and this is a non-empty, okay, if H is a non-empty subset of this, H is a non-empty subset of G. So simply this H is said to be subgroup. H is said to be subgroup if it holds this property. It means for every A belonging from H and B belonging from H, so simply A inverse will also belongs to H if it is a group. Then A star B inverse is also belonging from H. This is the simple property. Now we'll say how it will work. So simply, first of all, if there exists any, so this property means that you are taking two elements from a set. If you are taking two elements from a set, it is it is satisfying the closure property, which satisfies the first property of group. Inverse of each and every element there exists. It means that simply this property holds for inverse. It means each and every element have the property of inverse. That we can say also associative property. If it is a subset of G, it will by default it will hold the property of associative. And simply, what about the identity? So simply, if you have any subset from G, then A belonging from H and identity is belonging from H, and we know that the inverse of identity is nothing but identity. Okay, so if I will take A into A, identity inverse, that is simply is inside the H. So it means like simply instead of going for all those four property, we can check this one property that is known as A star B, and this is the one step test for subgroup. Okay, now we'll discuss some properties or some results on on the based of for subgroup basically. Okay, so for all m greater than equals to 0, all mz is equals to, okay, if I have any z which is nothing but a group of integers. Now we'll say what are the subgroup of this. So if my m is not equals to 0 and m is greater than equals to 0, then simply, or not equals to 0, simply I can write m is greater than equals to 0, all are subgroup. I will write mz, then all are subgroup of this z. Now, how can I define mz? It is simply I will multiply each and element of A, each and every element of z, that is known as A. Okay, so in this way this set will be defined. So these are the subgroup of. Now you will say, sir, what is the meaning of this? So simply I have one z here. So 2z, okay, z itself is a subgroup, of course. 3z itself also a subgroup. 4z is also a subgroup. 5z is also a subgroup. Okay, nz is also subgroup for this z. So this is the simple result here for group of integers. Next, H is a subgroup if and only if A star B inverse is, that's the simple one step test. Okay, this is nothing but one step test that we have already discussed. One step test. Next, if H is equals to identity and H is equals to G are always a subset. Now I want to talk about the types of subset that are very, very important. So simply, if I have any group G star, then there exist two types of subgroups. One is known as trivial subgroup. Okay, trivial subgroup is also known as improper subgroup, is also known as improper subgroup. Another one is known as non-trivial subgroup, or also known as proper subgroup. Now, what is the meaning of trivial? Trivial means by default. Trivial means by default. Okay, so what is the meaning of by default? So simply I want to explain you. If you have any group, like this, let's say it is your G, means if it is a group, it should contain identity. Let's say this is the identity, and I'm taking the subset of this group which contains only identity. Okay, so let's say this is H, and which contains, this is a subset of G and which contains only identity. So now from here simply I can say this is a set which satisfying all those properties. First one, but closure. If you'll take, okay, one thing, identity is unique for any group. There does not exist two identities for the group. Okay, identity is unique for group, but inverse is different for each and every element. Inverse is different. So now from here identity is unique. So simply it contains only one element. So if I'll take identity star identity, that's the same thing. Okay, same element is there, and simply there is one element in that set only, but identity is only one. So first property, that is what the closure property, it holds the closure property. Associative property, obviously it holds the associative property. Identity exists, and the inverse of identity is in identity itself. So that's what it is satisfying all four properties. So this identity is a subgroup of G. So now from here, why it is by default? If any group, you are taking any group, there exists identity. If I will take identity from that group, that's the subset of that, then it will be by default it will be a subgroup. And one another point, we know that set itself is a subset. If set itself is a subset and G is subset of G, and G is nothing but what? My group. So if G is my group, then it's simply, we can say that G is subgroup of G. So these are known as trivial and improper subgroup, means by default subgroup which are always exist for each and every element. And now one more thing, if any group is containing only two subgroups known as trivial subgroup, then that group is known as simple group. Okay, then that I will explain you next. One more thing, next, non-trivial. What do you mean by non-trivial? Other than all subgroups of identity and Z are known as non-trivial subgroup, or you can also say proper subgroup, that we'll discuss. Okay, so simply here identity and G itself are both always like subgroup of any group. Okay, next, if A belongs to G, then H is something known as generator. If you have now there is a concept of cyclic group. I want to explain this point. If you have any cyclic group, okay, cyclic group means there exists at least one element. A whose order is equals to order of group. Now I'm taking what? I'm taking the collection of all generators. Okay, the element whose order is equals to order of group, that is known as generator, and I'm taking the collection of all generator, that is also subgroup. Because we know that, and one more property that we'll discuss, the order of subgroup is dividing the order of group. Always this divides the order of group, that we'll discuss. So from here, if I will take any like subset, which is something called as a collection of all generators, that is what the subgroup of G. Okay, next, if H is a cyclic group of G, then H is equivalent to Z. Now if I have any, let's say any like infinite, okay, we know that Z is something but infinite group of integer under addition, like composition. So from here, if I will take 2 belongs to Z, okay, then it is something what? Order of 2. So if I will take 2 as a generator of cyclic group, then this is simply H is a cyclic subgroup of Z. Okay, then what is the meaning of this? So simply I will write 2 is nothing but it's written as 2. So now from here I can write like this: if each and every elements of M, so simply, so 2 into n, and n belongs to this n, so I can simply write this is what? My m into n, so that is what? 2 into Z here. That's what I explained you. If you have any group Z plus, we know that Z plus was the integer, group of integer is always a group. Okay, Z plus is always a group, and mz, which my m is greater than equals to 0, are always a subgroup. For the simple criteria here. Okay, and simply you can write it for any of the number. Okay, next, one more thing, H is equals to H into H. Okay, H is equals to H containing all X, where X square is identity. X square is identity, is subgroup of G, where G is abelian. So simply you can take cleans 4 group. If it is a cleans 4 group, what are the elements? Then identity A, B and AB, and we know that what the property is, what? A square is equals to identity, B square is also identity, AB is also identity, AB square is also identity. Okay, so from here, if I will take any element, let's say A, the subgroup, and this is the abelian group kind of thing. Okay, and now 2 more important properties are there. These are basically we can say the algebra of subgroups. Now what do you mean by algebra of subgroup? First of all, one thing. Okay, what is the meaning of algebra of subgroup? So algebra of subgroup are basically for sets. There are certain algebras. First one is what? Intersection, union. Okay, so first I'll discuss what? Intersection. I'll discuss it. First I'll discuss intersection. What is intersection? So if you are going to take intersection of 2 subgroup, let's say I have 2 subgroup H and K of any group G. If I will take intersection, then H intersection K. Okay, it means I'm taking the intersection of the properties. Intersection means what? If The properties which are inside H and which are inside K, I am taking the common properties, and of course H and K both are subgroups, both are satisfying 4 properties. If I'll take intersection, then it is again a subgroup of G. Okay, now next property, next is what I'm talking about, union of two subgroups. Let's say if I have H and K, both are subgroup of G. Now I'm talking about union. It means H union K. This will be subgroup or not. It is not necessary that it will be always subgroup. Okay, now then when it will be a subgroup, there are two conditions, or we can say one condition. If and only if one contains in another. What is the meaning of this? One contains in another means simply if H is subset of K, or simply K is subset of H, or directly we can say H is equals to K. There are 3 properties are there, and all are OR property, not AND. H contains in K, it means that H is a subset of K, again K is a subset of H, or we can say simply that K is equals to H. Now it means we are taking the union. Whatever the property present in one set, it may be or it will be inside the union. Okay, we are not taking the common property, we are taking all the properties. So in that condition, H union K to be a subgroup, it should satisfy some properties, that is what the H subset of K or K subset of H, or simply H is equals to K. These are very, very important algebras of subgroups. Okay, next, that is very important, and sometimes the questions may arises from this particular part, that is what, counting of subgroup. Okay, it is very, very important. Now, what is the meaning of counting of subgroup? So number of subgroups. Okay, if they will give you some groups, for example Z, they will give you the subgroup. Okay, so, sorry, they will give you the group. So if they will give you the group G star, and they will talk about how many number of subgroups are there, how many number of cyclic subgroup, how many number of non-cyclic subgroup. If it is a cyclic subgroup, then we can talk about the abelian subgroup. Okay, then that thing we'll discuss here. So it is very, very important to discuss this thing, that how many, or basically we can say about the counting of subgroup, how many cyclic subgroups are there. Now it is very, very important how many cyclic subgroups are there. So if you want to talk about basically the counting of subgroup, then number of subgroup is equals to tau n. Now tau is what? Number of divisors. It is very, very important, and in the basics video of the group theory, you can go to my playlist and you can check how to find the tau n. So what is the meaning of tau n, that I will explain you. So from here I will take the example of Z6. If you have Z6, then number of subgroup of Z6. Okay, and basically number of subgroup of cyclic group. That's the simple, because it is the cyclic group. Okay, so now here it is equals to tau 6. It is equals to tau 6. What is the meaning of tau? So first of all, just write in a prime factorization 2 power 1 into 3 power 1. Now take the power 1 and add 1. Take the power 1 and add 1, just multiply this, you will get 4. So 4 number of cyclic subgroups are there. Now if a group G is cyclic, so simply here, if a group G is cyclic of order 100, then how many cyclic subgroups are there? Okay, so it means this is simple. This is simple. You have Z 100. Okay, I can take it as equivalent to Z100. Okay, I can take it as equivalent to Z100. So now I'm talking about the number of cyclic subgroup of this group is equals to tau 100. So just write in prime factorization, that is what, 2 square into 5 square. Write the power 2 plus 1 and 2 plus 1. Okay, so simply it is what, 3 into 3. So 9 cyclic subgroups are there for this Z100. Okay, we can take another example like this. So this is what the next. Now it has some properties or some more important results are there that we will discuss. Subgroup of abelian group is abelian, but converse need not be true. If you have any subgroup, now what is the meaning of abelian subgroup? What is the meaning of abelian subgroup? So what is the meaning of abelian group? It means there exist x and y belonging from G, then x star y is equals to y star x. That is what the commutative property. Now if you have any abelian group, then if the subgroup of abelian group is abelian. Now, but converse need not be true. It means that its subgroup of abelian group is abelian. Okay, now it means if a group has abelian subgroup, then the group may not be abelian. Now that's the very simple. We can take the counter example from here. What is the counter example? D4. Do you know that D4, that is what the R0, okay, R90, R180, R270, okay, and H, V, D and D dash. That's what the horizontal, vertical, diagonal and anti-diagonal. So now from here, I will just simply write that H is equal, like H belongs to D4. This is the horizontal. H belongs to D4. Let's say, okay, let's say K is a subgroup, that is what H, horizontal, is cyclic subgroup of D. It is what? It is what? Cyclic subgroup. Why it is cyclic subgroup? One thing, it is a generator of this. Using this horizontal, we can generate whole group. First one thing, abelian, it can be commutative with all. But the thing, we know that D4 is not an abelian group. Okay, D4 is not an abelian group, but this group is cyclic group. If it is a cyclic, then it is, of course, it is an abelian. So it is the counter example. Okay, D4 is non-abelian group. Okay, so simply. Okay, so first property is that. Next, if all subgroup of G is abelian, okay, if all subgroup of G, if simply we'll write if all subgroup of G, yes, if all subgroup of G is abelian, then G is an abelian group. Now, one more thing, important thing, all subgroup of G, if all subgroup of G are abelian, that's very important. All subgroup of G are abelian, then the group is abelian. Next, subgroup of cyclic group is cyclic. Subgroup of, from here, subgroups like subgroup of cyclic group is cyclic, but converse need not be true. It means we should give a counter example for this. Converse may not be true. If you have any cyclic group, okay, one thing, simply D4 is also the converse for this. It has a cyclic subgroup, but it is not an abelian. If it is not abelian, then it is not cyclic. That's very simple. Okay, if all subgroup of G are cyclic, then G is cyclic. Now I want to conclude these all result. So first one, what is first result? What is first result here, that I will explain you. The first result is this: if G is abelian and G is cyclic. Okay, G is abelian, then all subgroup are abelian. Okay, but converse may or may not be. Converse may or may not be. May or may not be true. Next thing, if it is a cyclic, then all. Okay, one more thing. So from here, one more thing. True. From here, true. Now we'll say, sir, why? Abelian group, all subgroups are abelian. If all subgroups are abelian, then abelian group. Okay. If it is a abelian, then some subgroup. Okay, from here, one more thing. If some subgroups are abelian, then it is may or may not be. May or may not. If it is all subgroups are abelian, then of course that group is abelian. And the same thing is here. If all subgroup are cyclic, all subgroup are cyclic, then Z is cyclic, then all subgroup are cyclic, and this is also true. But what about some subgroups are cyclic? Then it is what we can say, may or may not. Okay, simply, what about this? May or may not be. That's what the simple result here. Okay, and what are the counter example? You can take the counter example for D4, where subgroup is H, and the same example you can write here. D4 where subgroup is H, horizontal. Okay, this is a cyclic subgroup. This is a cyclic subgroup. If it is a cyclic subgroup, then of course it is a abelian subgroup. It is a cyclic subgroup, then of course it is a abelian subgroup. Okay, now next result here, one more result here that is very important. What is that result? Number of cyclic subgroup of order D in any group G is equals to number of element of order D in G divided by phi D. What's the meaning of this? If you want to calculate number of subgroup of number of cyclic subgroup, number of cyclic subgroup of D in G is equals to number of element of order D, number of element of order D divided by phi D, Euler phi D. For example, we'll take let's say, I think, okay, we have example here. We can take it from here. So how many subgroup of order 2 for this? How many subgroup of order 2? So what is the solution from here? What's the solution? First of all, we know that any subgroup of order 2 is cyclic, then subgroup of order 2 in this is also cyclic because it is a cyclic. Okay, now one more thing. Is it a cyclic or not? That we'll discuss later. But one more thing is here. Okay, discuss it. Yeah. Any subgroup of order 2 is cyclic. Any subgroup of order 2 is cyclic. Okay, then the subgroup of order 2 of Z8 cross Z2 is also cyclic subgroup. This is one more result, you can take it as result. Any subgroup of order 2 is always cyclic. So now I want to calculate the number of subgroup of cyclic of order 2. So first of all, I want to calculate what number of elements of order 2, okay, in Z8 cross Z2. How? Divisors 1, 2, okay, 1, 2, and then 4 and 8. Divisors of this 1 and 2. Now whose LCM? Take the pair. 1 comma 2. Its LCM is I want to take the LCM is 2. Then LCM of 2 comma 1 is 2. Then LCM of 4 comma 2. So take phi 1. So from here phi 1, phi 2. Okay, from here phi 2, phi 1. From here phi 4 and then phi 2. Find the value. It's simple. What's the value of this? It's going to be 1. It's going to be 1. And from here it's going to be 2 to LCM of okay, wait. Sorry. It's 4. It's 2 only. So from here phi 2 comma phi 2 is also 1. So total 3 element of order 2. Total 3 element of order 2. It is 3 divided by phi 2. So it means 3 by 1. So 3 subgroup of order. How many subgroups are there? 3 subgroup of order 2. Now what are those that we can easily find from here? 3 subgroups of order 2 you can find from here. Yes. So what are those? First one. Then we'll write then Z8 cross Z2 has 3 subgroup of order 2. What are those? 0, 1 belongs to Z8 cross Z2. That simple. H1 we can write 0 like this, 0, 1. Now from here we can simply write 0, 0 and 0, 1 because identity will be there, of course, because if identity is not there, then we can't write. Now 4, 0. What is that? Z8, Z2. That is basically Z2 is something we can write 4, 0, and what is the subgroup? 0, 0 will be there and 4, 0. Now you can say it is abelian also. If we'll take the addition, it will be same. It will be commutative. 4, 1. Z8, Z2. That is H3 is what? 4, 1. We can write simply 0, 0 because identity will be there. It is a group. Okay. These are the subgroup. Now some results are there. We'll see. If D is equals to, if D is equals to, okay, so simply we'll write from here. If D is greater than 0, if D is greater than 0 and D divides N, then number of subgroup of order D in Zn is unique. What is the meaning of this? What is the meaning of this? That we will see. Wait. It is saying that D is greater than of Z and D divides N where N is nothing but Zn. Okay. Then it is saying that subgroup of order D, subgroup of order D is unique means 1. How? What is the meaning of this? So subgroup of order D is equals to number of element of order D. Number of element of order D. It means what? Number of element of order D is what? Phi D. That's simple. Okay, I'll show you. And divide by phi D. So this is what? Number of element of order D. If D divides this, for example, Z2. It is Z2. And I'm talking about D, order 2. So 1 and 2. Only one element will be there. Na? Only one element. I'm talking about this. If it is a divisor of this or not, then it is what? Phi of. Now how many element of order 2? That is what? Phi 2. And I'm dividing also with phi 2. So phi D divided by phi D, that is going to be 1. It is nothing but unique in number. Only 1. So Zn has unique subgroup of order D. If it is a divisor of this, that. Next result. Z has an element of order D, then G has subgroup of order D, but converse need not be true. That's simple. Let's say Zn. Let's say Z3. G has element of order. It has element of order 3. Yes. It has element of order 3. Then it has subgroup of order 3. Yes. But converse need not be true. It means if Z has subgroup of order 2, has subgroup of order 2, it is not necessary that it should be the divisor. It should has element of order 2. Okay, that's the simple meaning here. So this is the result here. Next. Okay, next come to here. One more example that we can also see, that is what if I will take Z2 cross Z4. Okay, Z2 cross Z4 has subgroup of order 8. Okay, itself, and but it has no element of order 8, because if you will take LCM, it does not have LCM 8 from anyone. It does not have an LCM 8, but it has subgroup of order 8. Okay, next one theorem is here. That is what? Lagrange's theorem. It is what? Lagrange's theorem. If G is finite and H is a subgroup of G, then order of subgroup divides order of G. Order of subgroup divide order of G, but converse need not be true. Simple. An. I'll talk about an. What is the order of an? What is the order of an? That is simple, n factorial by 2, and order of Sn, that is simple, n factorial. Okay, clear or not? And every time it is a divisor of this or not? It's a simple. It means order of Sn divides by order of An, that is what, n factorial divided by n factorial by 2, and that will be 2 every time. You can see A4 is subgroup of S4. Then what is the order of A4? That is what, 4 factorial upon 2. 24 by 2 means 12. What is the order of S4? That is 4 factorial means 24. So 24. So 12 divides 24, that is 2. Yes or no? Okay. So this is what the simple thing. But converse need not be true. It is not like that every time if it is dividing, then it has what? It is a subgroup. So for example, 6 divides 12. But A4 has no element of order 6. 6 divides 12 because what is the order of A4? That is 12. But divisor is also 6. But it does not have any subgroup of order 6. Okay, so converse need not be true. Okay, next. Now we will say what are the subset of, what is the A4 that we can easily find. We will not go inside that, but this was the theorem. Just go on that. Yeah, note negation of Lagrange's theorem. Now if D does not, what will happen if D does not divide of order Z, then Z has no subgroup of order. That is what the truth. So simply it is. Now what is, I will give you the okay, I first let me explain this, then I will discuss what is that converse and what is this negation. Very clear, it is very clear and is very different. So negation, how? Now my question is, D does not divide order of Z. What will happen? Then of course it does not have any subgroup of order T. First, what is the Lagrange's theorem? What is Lagrange's theorem? D divides order of group. It has D divides order of group. Okay, no, wait. Yes, first, Lagrange's theorem says that order of H divides order of group. Converse is what? Okay, from here I'll simply write. Any number divides order of group. Let's say any number divides order of group, and it is not necessary that this group has subgroup of that order. And now if any number does not divides order of group, then of course it does not have any subgroup of order that number. For example, simply 3 is not divisor of 10. 3 does not divide 10. It means that any group of order 10 has no subgroup of order 3. That is the simple meaning. Okay, so come to the next point. If G is finite abelian group, then D divides order of group, then G has subgroup of order D. If it is a finite abelian group, it is what? The converse of Lagrange's theorem. If any number divides the subgroup, it's not necessary that it has the subgroup of order D. But if it is a finite, it's very important. I want to tell you, it is very important. If it is a finite abelian group, then the converse of Lagrange's theorem true. If G is any finite cyclic group, then if D divides Z, then it has unique subgroup of order D. it has unique subgroup of order D. So from here I will show you first one. An is not okay. First one, from here finite abelian group we can take Z3 or Z10. Now 3 does not divide 10. It means it does not have any subgroup of order 3. Next, 5 divides this. 5 divide 10. It means that 5 divide 10. It means what? It is what? Cyclic group. Okay, it is a cyclic, and simply we can say finite cyclic group. Then means it has unique subgroup of it has subgroup. Yes, it is a abelian also. It is abelian also, but in addition it is also cyclic group. It has unique subgroup of order 5. Has unique subgroup of order 5. Okay, so this is very important result here. Now we'll discuss group, or basically subgroups of order from subgroups of order 1 to 8. I'll show you each and every subgroup of order 1 to 8. Okay, we'll discuss one by one each and every subgroup, and I'll discuss also what is simple group and what are the proper and improper subgroups. Okay, that I explained you, but I'll show you how it will work here. So subgroup of order 1. We'll start with order 1. Okay, we can consider Z1 always abelian and cyclic. Okay, we'll see all the properties. What is the subgroup? Simple. Z1, it is what? Trivial, and also we can say identity, or we can also say improper. Okay. And it is also cyclic. This is also cyclic and abelian subgroup. Now what about order 2? What are the group of order 2? That is very simple. You can simply see from here that are Z2. This is we can consider as cyclic, abelian. So 2 elements are there. First one Z1, that is simply identity, and Z2 itself. Okay, so these both are trivial, or we can say trivial and improper. Next, both are cyclic also. Both are cyclic and abelian. Now come to order 3. So group of order 3, that is Z3. Now what is Z3? It is what? Subgroup. It is also cyclic and abelian. Identity, simply what? Z1 and Z3. Both are trivial and cyclic. Now this group is known as simple group. Why simple group? One more thing, prime order. This is also simple group. We can write this is also a simple group. It has 2 by default subgroups. Okay. Next, order 4. We'll discuss group of order 4. One possibility, that is Z4. Okay, one possibility, that is Z4. It is cyclic and abelian. One possibility, that is K4, that is abelian but non cyclic, abelian but non-cyclic. Okay, so what are the subgroups? That is Z1, Z2 and Z4. These both are trivial, or we can say improper, but this is what proper, or we can say non-trivial. Okay, now what about this group? Subgroup are identity. Subgroups are what? AB. Okay, A, B, AB. Okay, so in this way we can write what are the subgroups. So from here, identity is subgroup of order 1. Pairs, we can take AB, BA. Okay, so pairs are pairs of order, like order of subgroup. So 2 order subgroup is there, like identity and A, identity and B, okay, identity and AB. These are order 2 subgroup, order 1, order 2. And order 4 subgroup is what? K4 itself. This is what order 4 subgroup. Okay, so K4 is also, and this is what order 4 subgroup. So all are non-cyclic, all are abelian. All are abelian. Next, order 5. Group of order 5. What is the meaning of order 5? Order 5 group, because it is a prime, always cyclic. Z5, always cyclic and abelian. If it is cyclic and abelian, it is a prime. So Z1 and Z5 are only. And this is also what? Simple group. If it is simple group, it means both are my trivial or simply improper subgroup. Improper subgroup. Now order 6. What is the meaning of order 6? So from here we can see order 6. Cyclic and abelian. Two group will be there. Sorry, cyclic and non-abelian. So order 6. So first one, cyclic and non-abelian. If it is a cyclic, then of course it is abelian. So we can consider as Z6, or we can consider as S3, whose order is also, the order of S3 is 6 also. What is the subgroup? Z1, Z2, Z3 and Z6. Okay, Z1, Z2, Z3. So from here, this and this are known as improper. But what about this and this? These are proper. Okay, now what about S3? So it has, what is the order? What is the divisor? 1, 2, 3 and 6. It has subgroup of order 1, that is known as identity. Order 3, that is S3 only. Okay, now one more, I can consider it as H1, H2. These are both proper. Now what about improper? H3, that is identity and 1, 2. H4, identity and 1, 3. Okay, not comma. Comma is not here. Wait. So these are H1 and H2. What about H3? H3 is identity and 1, 2. H4, identity and 1, 3. H5, identity and 2, 3. H6, these are order 2 subgroup. Order 2 subgroup. Order 3 subgroups are there. That is what? Okay, wait. Order 2, number of cyclic subgroup of order 2, that is 3. Okay. Number of cyclic subgroup of order 3, that is 2. That I will show you. So identity 1, 2, 3, then H7. Oh no, no, no. Yes, 1, 3, 2 is also there. Now, from here, if question arises, cyclic subgroup of number of cyclic subgroup of order 2 in S3. So first of all, order 2 element. How many order 2 elements are there? So it is what S3 means 3. What is cycle decomposition? 1 plus 1, 1 plus 2 and 2. So this is LCM is 2. So here it is what? 3 factorial 1 into 2. So it means 3 elements are there. So this is what? Number of element of order 2. So now this is equals to 3 divided by 5 2, and that is what? 3. So 3 subgroup of order 2. So simply one more question is there. Number of cyclic subgroup of order 3 in S3, that is equals to, so how many element of order 3? So 3 factorial upon 3 factorial, that is 2. That is 2. Okay. So from here it is what? 2 upon pi 3. Okay. So 2 upon pi 3, and that is equals to 2 upon 2. So one element of order 3, that is H6. It is H6, and it is what? H3, H4, H5 are order 2, and this is order 3 subgroup. Okay. This is very easy. Now come to order 7. Order 7 prime number always order 7. So it is a prime number. So Z7. Okay. It is a prime number, always cyclic and abelian. Got the simple, and it is also simple group. Z1 and Z7, and also this is known as simple group. Okay. So Z7 is also simple group because it has 2 subgroup only. Next, what about order 8? First one, Z8. Okay, first one we all know, that is Z8 means what? Cyclic and abelian. But one more thing, Q8, that is what? Non-abelian. Okay, so from here, what are the subgroups? Z1 and Z8. Both are trivial, or simply we can say improper. Next, other one, Z2 and Z4. What about this one? Q8. H1 is identity. H2 is identity. Okay, H1 is identity. H2 is 1 minus 1. H3 is 1 minus 1 iota minus iota. Then H4 is 1 minus 1, because it is what? Identity is equals to 1 only. Okay. So this is 1. 1 and minus 1 will be there. And J and minus J. Then H5, 1 minus 1, K and minus K. H6 is Q8 itself. There are 6 elements. Okay. So from where these 3 are cyclic? Okay. From where these is also cyclic. These all are cyclic subgroup. These all are cyclic subgroup, and these are proper subgroup. Cyclic subgroup and proper subgroup. Okay. One more thing. So from here, order 6. Okay, order 8 element. So these are 2 possibilities for order 8 that we have already discussed. Now come to some specific groups. Subgroup of Dn Okay, that we will discuss here one by one. These are very, very important. So first of all, what are the, like, we'll take the subgroup of Dn. We'll start with the subgroup of D4. So first of all, we'll write what is D4. So D4 is simply simply what, R0, okay, R90, R180, okay, R270, H horizontal, vertical, diagonal, and anti-diagonal. Then order of D4 is equals to 8, 2n. Then by Lagrange's theorem, possible order of subgroups. By Lagrange's theorem, we can find what? Possible order of subgroup. What are that possible order of subgroups? 1 divides 8, 2 divides 8, 4 divides 8, and 8. Okay, so these are possible, not necessarily possible. Then D has element of order 1. And one more thing, D4 has element of order 1, order 2, and order 4. Then it is simply D4 has subgroup of order 1, 2, and 4. There is no subgroup of order 8. Okay, and now one more thing, number of subgroup of order 1 in D4 is equals to phi 1 divided by phi 1, that is unique. Okay, number of order subgroup, that is what the simple H1, simply we can say H1 is equals to R0. Now number of subgroup of order 2, that we all know, because it is what, even. If it is even, then number of element of order 2, that is n plus 1, means 5 elements are there. So number of subgroup of order 2 in D4. So what are the number of element of order 2? If it is, see, if n is even, then n plus 1, it is for even. If n is odd, then only n. Okay, these are the number of or element of order 2. Then it is 5 divided by phi 2, then it is 5. Now what are those? You can simply write what are those. So from here I will write H2, that is R180, H3, that is what, H, okay, H4, that is vertical, H5, that is diagonal, and H6, that is anti-diagonal. So 5 subgroups are there. And now phi 4, order of element 4. So simply now from here we can write number of subgroup of order 4 in D4, that is what, phi 4 divided by phi 4, because number of order 4 is 1, that is 1, and that is what, R7, R90. So we can simply write R0, R90, R180, and R270, the subgroup of order 4. Okay, so this is what. And now non-cyclic subgroup of, this is what the cyclic, that we have found cyclic subgroup, because that's the formula for cyclic. What about non-cyclic subgroup of order 4 in D4? Okay, so let H dash is equivalent to Z2 cross Z2. because it is non-abelian. Okay, it is abelian but non-cyclic, because LCM is, because GCD is not 1 here. So H dash has 3 element of order 2. Okay, H dash has 3 element of, now how, see, I can take D4 is equivalent to this. D, basically it is 8. Okay, D4 is equivalent to Z4 and Z2, and this is a subset of this, a subgroup of this, from where I can take 3 elements here, and simply I can take it from here, that is H1. Okay, so from here I can take H dash is nothing but 4 elements are there, R0, R180, H and V. Okay, and also I can take H2 dash. Okay, this is H1 dash. I can take R0, R180, okay, D and D dash. So simply we can take so many elements from here. Okay, next, what about the subgroup of D3? Okay, before going to this, we can also find, like in this same manner, we can also find subgroup of D3. Now we'll discuss subgroup of Sn. So from here we'll discuss subgroup of Sn, then subgroup of CUET, and so many things are later there that we will discuss. So subgroup of Sn. What are the subgroup of Sn that we will simply see? So first one S1 is identity. Okay, so S1 has element of order 1 only. So it means what? Number of subgroup of order 1 are phi 1. Okay, how many element of order 1 are 1 and phi 1? That is only 1, and that is known as only identity. Simply I will write identity or itself S1. Okay, next S2. It has 2 element, identity or identity and 1 2. So from here, number of subgroup of order 1 and 2. That's very simple. So from here, order 1, that is H1, that is going to be identity only. Okay, that is identity only. What about H2? That is 1 2 means identity and 1 2. It is simply identity. What about S3? What about S3? That we will discuss. I discussed already for S3. Okay, so S3, it has identity 1 2 1 3. Okay, 2 3 1 2 3 1 3 2. I discussed H1 is identity, H2 is identity and 1 2, H3 is identity 1 3, H4 is identity and 2 3, H5 is identity 1 2 3 and 1 3 2. These all are 2 order. This is order 1, this is order 3, and H6 are S3, this is order 6 subgroup. Okay, now come to that I have already discussed. Now come to subgroup of Q8 that I have already discussed. So subgroup of Q8, okay, this is what? Plus minus 1, plus minus I, plus minus j, plus minus k, already discussed. Next, subgroup of order 9 of Z3 cross Z15. Subgroup of order 9 in Z3 cross Z15, how can we find? So from here we will see subgroup of order 9. So first thing, what is the order of subgroup? Is 9. Now what is H here? 9 means it can like this, or what are those possibilities? Z3 Z3. Okay, so if H is this, then H has element of order 9. What about this? It is 3 cross 3. It does not has H. It does not have any element. Does not have any element of order 9, means it does not have subgroup. So it is simply Z9. So if it is Z9, then so my H is simply H is equivalent to Z9, not equal, equivalent to Z9. Then Z3 cross Z15 has element of order 9. What about it has or not? Means this 9, like if it is a subgroup, necessary condition is that Z3 cross Z15 should have element of order 9. Then it is 1 and 3. Divisors are 1, 3, 5 and 15. Any of the pair has LCM 9? No. It means that it has no element of order 9. Okay, it has no element of order 9. And now what about this? Wait, one more thing. So from here it does not. So H can't be this. So H is this only. Yes. Okay. Wait. 9 3 3 LCM 3 9 1 3. If we'll take LCM, this 3 comma 3, then 1 1. But it does not have LCM of 3. Okay. So H is something like this, but it does not have 9. So it means it does not have any subgroup of order 9. Okay. Next. What about order of 9 in Z6 or 15? So from here, what is H is equivalent to Z9 and is equivalent to Z3 cross Z3. Now what about this? So from here, Z6 cross Z15 has no element of order 9. Okay, why this is it does not have element of order 9, but it does not have element of order 3. Yes, and it has also element of order 3. Then this is a subgroup of this. Okay, and again this is also subgroup of this because it has element of order 8. H has 8 element of order 9. Okay, this has 8 element of order 9. So from here, how? So simply 1 3 1 3. What is the pair? 1 3 has LCM 3. 1 3 has LCM 3. Wait. Yes, 1 3 has LCM 3 and 3 3 has LCM 3. And it has also simply you will just take it like this. What is the divisor? 1 2 3 and 6. 1 2 not 2. 1 3 4 and 1 3 5 and 15. The divisor. Now if we'll take, we will get LCM as 9. For 6 and 9, LCM is 9. Okay, so yeah, so simply from here H has 8 element of order 3. How many elements are there? 8 element of order 3. So simply I'll write it has 8 element of order 3. Okay, and it has exactly 8 element of order 3. Unique element of, yes. From here unique, so 9 elements are there, na? So from here unique element of order 3. That's what the simple, you can easily you can see from here easily. That's what the simple criteria means, that it has element of order 3 and it has element of order 3. Okay, means 9 means that this set, just see this set, and it has an element of order 3, it has also element of order 3, and simply from here it has element of order 3, yes, but it does not have element of order 9 still. Okay, so from here it is also correct answer. So Z3 cross Z3 is this subgroup. Next, product of two subgroup. No, so from here we'll just see product of two subgroup. Let H and K are two subgroup, then product of two subgroup are defined as like this. This is what H and K. So element, we'll take the multiplication as element. Okay, multiplication is element wise. And one more thing, property is there. Order of H into K is nothing but order of H into order of K divided by order of H intersection K. Again, H and K are two subgroup, then HK is also subgroup of this. And HK are two subgroup, then HK is subgroup of G if and only if it is a subgroup. Now H and K are two subgroup of G, then it has if it is commute to each other. Okay, this is very important here. Next, subgroup of general linear group that are very important. Now there are two cases in subgroup of general linear group. Yes. So if it is a like G is equals to general linear 2 and field is 2, how many subgroup of order G? So simply I will just write this group as equivalent. It is what, 6? What is the order of this group? Simply what is order? The order of this group is 6. How will you find the order of group? It is very simple. So 2 power 2 minus 2 power 1. Okay, 2 power 1 minus 2 power 0. This is what, 4 minus 2, and it is what, 4 minus 1. It is what, 2 into 3. Order is 6. So 6 means I can write it as Z6 and S3. Now we know that general linear is a non-abelian group. Okay, so this G is here abelian, not abelian, means it can't be a cyclic, means it is equivalent to S3. Now how many subgroup of S3? How many subgroup of S3? That we know that H1 is identity, then H2 of order 2, H3 of order 2, H4 of order 2. Okay, these all are order 2, H5 of order 3, H6. So total 6 subgroups are there. So in this way you can find so many things here. Okay, so now we have some questions are there that we will also discuss from here. So first question, if order of group simply like this from here. Yes, so if order of group is 4 and every element of G has self inverse, then find the number of subgroup in G. So from here, how can we find? So these are some questions here. So given that this is simply equals to, now I can consider G as Z4, G as Z2 cross Z2. Now one more thing, it has self inverse, and it is not like that. It is not necessary that every time this says equivalent to Z4 means this is Z2 cross Z2. So from here we can easily find this. Next question, order of A square is equals to order of B, then order of A is equals to order of B. Okay, so what is this? It means we can take any element from D4. We can take the element of D4. So order of A square, then order of R180 square is equals to order of R0, that is what, 1. And what is the meaning of order of B square? So here order of B square is order of R0 square is order of R0, that is also 1. Then order of A square, simply here order of A square is equals to order of B square. Now what about order of A and order of B? So from here order of 180 is not equals to order of 0. It means that order of A is not equals to order of B. So it is not true. It is not true. Next, one more question is there. It is saying that if A square is equals to B square, then order of A is equals to order of B, yes or no? So simply we'll take A is equals to R0 and B is equals to R180. So what is A square means R0 square is R0 only, and what is B square, that is R180 square is R0. So it is simply A square is equals to B square, but R0 is not equals to R180. It is also not true from here. Okay, next some results are there. If any group of any order of group is P into Q, then P less than of Q, then like G has unique subgroup of order Q. That is simple. Okay, it means what, 2 into 3. Okay, 2 into 3. What is P? P less than Q. So P is 2 less than 3. Then it has unique subgroup of order 3. Okay, next order of 21, then 7 into 3. So 3 less than of 7. Then it has unique subgroup of order 7. Now if it has unique subgroup of order 7, okay, unique subgroup of order 7, then it has what, how many subgroups are there? 1, 3, 7 is also divisor, and 21 is also divisor. So unique subgroup of order 7, then remaining all are order 6. So from here we can simply find number of element, that is 14. 14 divided by 3, then 14 by 2, so 7 subgroup of order. This is order 3, 7 subgroup of order. Okay, next, if it is in P into Q, then P is less than of Q and it is a non-abelian group, then G has Q subgroup of order P. Q subgroup of order P. So from here I'll take one example. It is a non-abelian. Now G is what? Non-abelian. In the previous one G was okay, that was not specified. Now it is a non-abelian. So what? 3 into 2. So 2 less than of 3. Okay, so from here 2 less than of 3, it means Q subgroup of 3 subgroup of order 2. 3 subgroup of order 2 are there. Okay, so 3 subgroup of order 2. Next, order of group is P square. Then how many subgroups are there? That's the very important. If it is a P square, order is P square, then it means order of group is equals to P square. Then simply what can I do from here? ZP square, or simply what? ZP cross ZP. Then it means tau P square, and that is what? Number of subgroups. That's the simple. 2 plus 1, 3. It is P square, then 3 subgroups are there. Is what? Simple. So if G is equivalent to ZP cross ZP, then it has subgroup of order P, 1, P and P square. And number of order of subgroup, that is what? P plus 1. So from here, number of subgroup of order 1 is equals to 1, unique. So number of subgroup of order P is something P minus 1, P plus 1 and 5P. So from here 5P. 5P is P minus 1. So it is P plus 1. Okay, and number of element of order P square, and that is what? Simply P square minus 1. From here we can easily, okay, sorry, that is what? 1. Simply 1 is what? 1. So here from here total 1 plus P plus 1 plus 1. So total subgroups are there P plus 3. Here it is 3 and here it is P plus 3. So this is all about subgroups and counting of subgroups and product of two subgroups. So thanks for watching my video. Keep watching MS Maths. Thank you. Bye bye.